Everyone knows bees are excellent pollinators, shifting pollen from one plant to another as they chug nectar and bring back food to their hive to feed their growing brood. Flowers put large amounts of energy into attracting bees with enticing flowers and sweet, sweet nectar. This explains why bees are attracted to pollen. But what attracts pollen to the bee?
Static electricity. Just like dragging woolly slippers on a carpet in the winter or rubbing a balloon through our hair, as the bee moves through the air, it gathers a positive charge that attracts and holds the negatively charged pollen to the hairs on its fuzzy little body.
If an individual bee can build up its own electric field as it buzzes through the air, what kind of charge can an entire swarm of tens of thousands of bees build up? Can they create an electric field powerful enough to affect the Earth's weather systems? Can understanding this effect allow us to use honeybees to predict natural weather disasters like tornadoes? Even more radically, could we one day build massive mechanical swarms to control these weather systems?
The Earth and its atmosphere are always electrified, with the surface holding a negative charge and the atmosphere holding a positive charge that gradually increases as you progress out, up to millions of amperes at the highest altitudes. This gradual increase is known as the vertical atmospheric potential gradient, for now called APG. Even though the charge is permanent, due to the conductivity of the air, the electrical field must be constantly maintained with various current sources, from large external forces like solar flares to more common local occurrences like thunderstorms.
The APG can be also influenced by diverse natural and human-caused events, such as the movement of tiny, charged particles from precipitation, volcanic eruptions, pollution, and, as a recent study shows, insect swarms.
Lead scientist Ellard Hunting and his colleagues placed electric field monitors near several honeybee hives ready to swarm. The scientists recorded these migrating swarms as they passed over the monitors and noticed a net positive increase in atmospheric electricity. Control monitors placed away from swarm activity detected no such increase. Using this data, Huntington calculated that charges generated by the honeybee swarms were significant enough to impact the APG.
Since bees are not the only insects to swarm, Huntington calculated the effect that various other insects, including locusts, cinnabar moths, and peacock butterflies, have on the APG. They found that honeybee and locust swarms both had a similar or higher charge density than thunderstorms.
So why does this matter? Why should we care that honeybee swarms carry such a significant charge?
Well, the atmospheric potential gradient influences a wide range of major and minor natural processes, from the seemingly unimportant but super cool phenomenon of flying spiders or seed and microorganism dispersal, to more pressing matters like weather and climate change.
Electric ecology is an expanding but still very understudied field. With the steadily increasing urgency for climate solutions, further understanding the APG's role in weather systems and the natural electrical interactions of insect swarms and other ecological phenomena could revolutionize meteorology and climate sciences. This could lead to an increased understanding of weather patterns and more accurate weather forecasts. Understanding is a step toward controlling these seemingly uncontrollable forces.